Adsorption of lead and iron from industrial wastewater using Melon, Citrullus Colocynthis, Husk Activated Carbon. Abstract: the application of activated carbon as an adsorbent in remediating heavy metals from industrial wastewater is increasingly being embraced. Agro wastes activated carbon adsorbents have proven to be more suitable and cost-effective than the conventional wastewater treatment methods for the remediation. In this work, the shell of melon husk, were converted into activated carbon and applied for the adsorption removal of iron, Fe2+, and lead, Fe2+, ions. The melon husk carbon were activated using NaoH, H2SO4 and CO, NH2, Urea, reactive agents. After which the adsorbent were then characterized using Fourier transform infrared spectroscopy, FTIR, and scanning electron microscopy, SEM. An adsorption study was then conducted. The wastewater were treated with activated adsorbent at a dosage interval of 0.2 g, between 0 and 1.0 g, with a reaction time of 0 to 100 minutes at 10 minutes intervals and at constant speed of 150 rpm. The characterization study indicates that the melon husk ask is suitable for use as an adsorbent, and the adsorption study indicate that the removal rate of these heavy metals varies with changes in activation method, contact time, and adsorbent dosage. On the effect of dosage, the melon husk activated carbon, MHAC, removed iron, Fe2+, ions between 6.39 to 2.81% for all activation agents at optimum dosage of 0.8 g. While 0 to 100% of lead, Pb4+, ions were adsorbed at dosage of 0.8 g for all activation agent except for H2SO4. On the effect of contact time, equilibrium for removal of iron, Fe2+, and lead, Pb4+, was reached at an average contact time of 70 minutes and 20 minutes respectively for all activation agent. It was thus concluded that the melon husk activated carbon, MHAC, was more effective for removal of lead, Pb4+, ions compared to removal of iron, Fe2+, ions. Keywords: activated carbon, adsorbent, wastewater, heavy metals, melon husk. Introduction. Availability of portable water is vital to the human race because it is essential for all life forms and energy. MHAC, ETAL, 2016, Nwankwo and Mogbo, 2014, Bhatnagar and Salanpa, 2010. Water also being a universal solvent has made it important for industrial usage. Due to the aforementioned reason, there is a tremendous increase in demand for portable water, but there is limited supply due to drought, overexploitation, and contaminations. MHAC, ETAL, 2016, Bhatnagar and Salanpa, 2010, Abdelraouf and Abdulrahim, 2017. Contaminations of these portable water is ascribed to discharge of industrial effluent, Nwankwo and Mogbo, 2014, discharge of untreated domestic sewage and lethal industrial wastes, and runoff from agricultural fields, Bhatnagar and Salanpa, 2010. Industrial effluent discharged from metal industries are sources of high concentration of heavy metal ions such as mercury, lead, tin, cadmium and iron. Corral Bobadilla, ETAL 2019. The release of heavy metal ions in water streams poses a risk of affecting the ecosystems because of their non-biodegradability and bioaccumulation. Ojedokan and Bello, 2016, Ajikwo and Martin, 2016. One of the heavy metal ions in our ecosystem that has raised serious concern is lead and iron. High accumulation of these metals has been identified to cause slight deficits in mental development, kidney problems, and high blood pressure. Ojedokan and Bello, 2016, Igwe, 2007. Thus there is a necessity for removal of these metals from our sources of portable water. A great deal of effort has been dedicated to the efficient removal of heavy metal ions. The commonly used methods for removal of metal ions from industrial effluents are chemical precipitation, coagulation, ultrafiltration, chemical oxidation, ion exchange, filtration, Electrolysis activated sludge etc., Ajala and Okwakwam, 2018, Jawa, ETAL, 2013, Radade, ETAL, 2017. However, some of these methods cannot effect complete removal of the heavy metal ions, are too expensive, are selective of metal for removal, requires high energy, requires high concentration of reagents and generate very toxic sludge. Suleiman, ETAL 2017. Activated carbon in adsorption of heavy metal ions has been gaining attention of researchers due to affordability and availability, simplicity in design and operation, high effectiveness in removal of heavy metals, generation of low toxic sludge and its adaptability for domestic and industrial wastewater. Madhu and Lajide, 2013. Activated carbon is produced from burning agricultural waste material like rice husks, coconut shells, melon husk, and palm oil shell, which are activated either by pyrolysis, chemical or physical process. Tata, ETAL, 2017. Activated carbon effectiveness in removal of heavy metal ion depends on its surface area, pore space and volume of ash content present. Mutagoa, ETAL, 2014. Melon husk is an agricultural byproduct which is readily available in abundance at no or low cost. The melon husk don't have an immediate use, they are either disposed as waste causing nuisance to the environment, feed to livestock or burnt as a form of disposal. This work aimed to use the shell of melon husk, which were converted into activated carbon and applied for the adsorption removal of lead, Pb4+, and iron, Fe2+, ions. 2 Material and methods. A. Adsorbent and wastewater. Melon husks were collected from the melon sellers at the Wasiu market in Ogbomoso, Oyo State, Nigeria. The materials were left and open sun drying for 3 to 4 days. Then, the material was washed with double distilled water several times to remove impurities. After that the material was again dried in oven at 1050 C up to 24 hours. The raw material was crushed into small pieces and prepared to fine grind powder by use of mixing grinder. After grinding the material they was sieved, 75 to 150 m, to achieve uniform particle size before it was used for characterization without any prior chemical treatment. The wastewater was collected from a blacksmith workshop at Isle, Itsha, Ojwakan off Odangba Road, Ilorin, Kwara State. B. Fourier transform infrared spectrometer, FTIR, analysis. The Fourier transform infrared, FTIR, spectrometer to determine the functional groups on adsorbent was performed at the Quality Control Laboratory of the Chemistry Department of University of Ilorin. In order to study the functional group of the adsorbent, an IR analysis was performed with the FTIR spectrometer, Nicolay Avatar 330, England. 1 mg of dried, finely divided adsorbent was mixed with 200 mg of Kabir and pressed using hydraulic press and mold. The mixture obtained was immediately analyzed with a spectrophotometer in the range 3500 to 500 cm1 with a resolution of 1 cm1. The influence of atmospheric water and CO2 were subtracted. See Scanning Electron Microscopy, SEM. The surface texture and morphology of the carbonized melon, Citrullus Colocynthis, husk was determined using scanning electron micrograph. The availability of pores and internal surface is a requisite for a potential adsorbent. To observe the surface pore structure of the activated carbons, SEM studies was carried out using electron probe microanalyzer, model JEOL JXA840A, Japan. For char samples, the foremost requirement was that they must be moisture-free. The pulverized sample was mounted onto a substrate with a conductive adhesive. Coating with a thin film of conducting material was the primary requisite for all non-conducting specimens to be examined in SEM. In the present study, conducting material coating of specimen was done with gold metal by vacuum evaporation to get uniform thickness of specimen study during analysis. D. Melon husk carbon activated by H2SO4. Seifel Azar et al., 2005, and Raghuvanshi et al., 2004, acidic activation method was used. The carbonized husk was treated with H2SO4 in the ratio 1:1, with V, and was dried, after which it was soaked in 1% NaHCO3 overnight to remove residual acid. It was then oven dried at 150 OC for 24 hours. Melon Husk Carbon activated by NaOH. Raghuvanshi et al., 2004, base activation method was used. The carbonized husk was soaked in 0.5 m NaOH for 12 hours. After which it was soaked in 1% formaldehyde, HCHO, at 50 OC for 4 hours to prevent any further color interference during activation and then dried at 60 OC for 2 hours. The NaOH activated melon husk was stored in an airtight container ready for use. Melon Husk activated by Urea. Nwankwo and Mogbo, 2014, activation method was used. 100 g of carbonized melon husks was soaked in 0.6 g/cm3 urea solution for 6 hours, drained and dried overnight at 50 OC and was further activated at 120 OC for 4 hours using memmered oven. The urea-activated melon husk carbon was stored in an airtight container ready for use. Heavy metal analysis. Flame atomic absorption spectrometry, FAS, is a simple and well-available technique for the determinations of heavy metals in the natural water samples. A Perkin, Elmer and HDR 890 colorimeter was used in this study. Atomic absorption measurements were carried out using air, acetylene flame, while Hatch colorimeter measurement test kits provided was used. The operating parameters for working elements were set or recommended by the manufacturer. Treatment of wastewater using the adsorbent. Batch adsorbent experiments was conducted to determine the effects of parameters such as adsorbent dosage, 0.2 g to 1.0 g at 0.2 g interval, and contact time, 0 to 100 minutes at interval of 10 minutes, on the sorption of lead, Pb4+, and iron, Fe2+, from aqueous solution using melon husk activated carbon. The batch experiment was conducted at room temperature and stirred with 20 ml wastewater sample in a 100 ml or Lenmeyer flask. After stirring, the suspension was filtered using Whitman filter paper and sample adsorbed was measured spectrophotometrically by using standard method of Sun and Shi, 1998, to determine lead, Pb4+, and iron, Fe2+, ions content. The amount of the lead, Pb4+, and iron, Fe2+, ions adsorbed, Qt, mg/I, at time, t, was calculate by using equation 1. Qt, mg/L, equals, co-Ce, *v/m, 1. Where Qt, mg/L, is the adsorption capacity of the melon husk activated carbon, Co, and Ce are the initial and equilibrium adsorbates concentration at a given time, T respectively, V, L, is the volume of the adsorbates and M, G, is the mass of the adsorbent. 3 results and discussions. A structural composition. Fourier transform infrared, FTIR, spectrometer analysis of the adsorbent was performed, and the percentage transmissions of various wave numbers were presented in Fig. 1. The FTIR spectra of the adsorbent showed the presence of amine RNH2, amino acids, protein, glycoprotein, carboxylic acids, fatty acids, lipopoly, saccharides, and phosphates. The characteristic adsorption bands of hydroxyl and amines of 3354.09 cm1, indicating the presence of exchangeable O and NH+ group respectively, alkyl chain at 2920.32 cm1, amides and phosphate groups at -1 to 1. 1026.91 cm and between 900.26 cm and 773.61 cm respectively, and PO vibration of moiety at 675.46 cm1. The adsorption bands identified in the spectra and their assignment to the corresponding functional group in the adsorbent could enhance the surface to which adsorption could take place. Fig 2a to Fig 2d show the scanning electron microscopy (SEM) image of melon husk carbon without any modification, with H2SO4 activation, with NaOH activation, and urea activation respectively. Fig 2. Scanning electron microscopy, SEM, images of melon husk. A. Without any modification, B. With H2SO4 activation, C. With NaOH activation, D. With urea activation. It was observed from Fig 2a that the structural composition of the melon husk carbon is densely packed and has some voids which indicate its ability to absorb metal ions from the wastewater. It was observed in Fig 2b that the structural composition of the activated melon husk with H2SO4 have large voids compared to that in Fig 2a, thus indicating a more likely effectiveness in adsorption. It was also observed in Fig 2c and Fig 2d that their structural composition has many smaller voids compared to Fig 2a, thus indicating more effectiveness in adsorption. The seaming rough surface of all the adsorbent is an indication of high surface area. B. Contact time effect. The effects of contact time on iron, Fe2+, and lead, Pb4+, ion sorption using different melon husk activated carbon were presented in Fig 3 and Fig 4 respectively. It is evident from Fig 3 and Fig 4 that the removal of iron, Fe2+, and lead, Pb4+, ions increases with increase in contact time, until equilibrium was attained, after which the sorption capacity started fluctuating below the maximum capacity. Fig 3. Effect of contact time on iron ions adsorption using different activated melon husk. Fig 4. Effect of contact time on lead ions adsorption using different activated melon husk. The adsorption of iron, Fe2+, in Fig 3, shows that equilibrium were attained at 60 minutes for urea activated melon husk, 80 minutes for NaOH activated melon husk and 70 minutes for H2SO4 activated melon husk, while for the lead, Pb4+, ions adsorption as shown in Fig 4, equilibrium were attained within the first 10 minutes for NaOH and H2SO4 activated melon husk and 20 minutes for urea activated melon husk. Therefore contact time can be optimized to 70 minutes, i.e. 1 hour, 10 minutes. See adsorbent dosage effect. The effects of adsorbent dosage on iron, Fe2+, and lead, Pb4+, ion sorption using different melon husk activated carbon were presented in Fig 5 and Fig 6 respectively. Fig 6. Effect adsorbent dosage on lead ions adsorption using different activated melon husk, 20 ml/70 minute. In Fig 5, it was observed that increase in adsorbent mass of each melon husk activated carbon leads to an increase in iron, Fe2+, ions removal until it reach an optimum adsorption point, after which further increase in adsorbent dosage leads to a decrease in iron, Fe2+, ions removal. The optimum adsorbent mass of 0.4 g was observed for H2SO4 activated melon husk carbon and 0.8 g for both urea and NaOH activated melon husk carbon. The optimum adsorption of iron, Fe2+, ions was 22.81% observed at 0.8 g adsorbent dosage of NaOH activated melon husk carbon. In Fig 6, it was observed the removal of lead, Pb4+, ions did not show consistent increase in adsorption process with increased adsorbent dosage as observed for iron, Fe2+, ions removal except for H2SO4 activated melon husk. There was fluctuation in the rate of adsorption of lead, Pb4+, ions with increase in adsorbent dosage for urea and NaOH activated melon husks. For H2SO4 activated melon husks, increase in adsorbent dosage increased the percentage adsorption of lead. Pb4+, ions until optimum adsorption point of 4 g adsorbent dosage was reached. The amount of ions bound to the adsorbent and the amount of free ions remained almost constant even with further addition of dose of the adsorbent. Con, ETAL, 2004, reported that the sorption capacity is dependent on the type of adsorbent investigated and the nature of the wastewater treated. This could be possible reason lead, PB4+, did not show strict dependency on the adsorbent dosage, especially with urea and NaOH modified melon husks carbon. The optimum adsorption of lead ions was 96.4% observed at 0.8 g adsorbent dosage of NaOH activated melon husk. Thus, activated melon husk is more effective in adsorbing lead ions. For conclusion. From the above discussed results, a few important conclusions were drawn concerning the structural composition and effectiveness in sorption of melon husk activated carbon. The structural composition analysis indicates a spectra band of potential sites for adsorption of iron and lead ions. Also, the rough surfaces and voids observed from scanning electron microscopy, SEM, images indicate the potentiality of melon husk activated carbon in treatment process of heavy metals. The sorption capacity is dependent on activation method, contact time, and adsorbent dosage. The melon husk activated carbon is more effective for removal of lead, Pb4+, ions than for removal of iron, Fe2+, ions.